Okay, yeah, hey, thanks everyone for coming. It's nice to see everyone. And if you catch me around later, feel free to say hi. I'm friendly. I will chat with you. I love to see what everyone is up to. So be friendly. And right, okay. So what I'm going to demo for you today is 11 examples where I'm going to walk you through the new async awaits primitives in standard IO that is upcoming in Zig 0.16.0, which will be released in 3 to 4 months. And there's more to get into, but this is a intro into the synchronization primitives that will then now be available to all of Zig code to use. And because it's kind of an intimate environment, it's okay if someone is kind of lost, you can interrupt me because we have time and this will be interactive. And so in the QA, it's not just QA. We can actually do a little bit of feedback. Like, sometimes in QA, it's not, you shouldn't express your opinions too much because it's rude. It's fine. Here, actually, in the QA, give me your opinions and we can have a dialogue because we have time for it. Okay. So put your critical thinking hat on while we do some of these things. Okay. Okay. So, to begin, first, let's try to keep it simple and understand the basics, and then we'll slowly add more asynchronous things into it. So, with our first example, there is nothing asynchronous happening here. This is effectively hello world in Zig, where we have our main function, we have our function called do work. Our do work function is actually just going to sleep. I just came from Italy, so now I'm thinking that this is what working looks like is sleeping. Uh, Loris told me that I had permission to make this joke. Okay, so everyone okay on this one? So simple? Okay. So next, we're going to set up a little bit. Still not using async await yet, but I need some tools in my toolbox before we really add the complexity in. Okay. So this code is the same, but now in the setup, maybe this code looks familiar to you. We set up an allocator. Okay. Now this is kind of like setting up an allocator. You set up an IO implementation. Now in this case, this is an IO implementation based on threads. So this is not using KQ. This is not using IOU ring. This is not using um, an event loop. It is a threaded implementation of the new standard IO interface. And this setup will be the same in all the examples. So now we can focus on our example code, which is the same as last time. So still nothing interesting. We just work, which of course is sleeping. Okay. Is anybody lost so far? This is where we start. Okay, good. Okay, next. What we've done is we've taken this function, do work, okay, and now we're using async await. So what async await means to Zig is you decouple the calling of a function from the returning of a function. So really just think of it like a function call, you call it, you wait for it to be finished, and then it returns. With async await, you split that apart. So calling is one thing, and then you can do something else, and then returning is another thing. It's the decoupling of these 2 points. That's how it works in Zig. So this code is the same as before. It's exactly the same because we didn't put any code in between here. So we're still just calling do work, except we split the call into here, and then we're just waiting for the call to finish. And the way that this API works is idempotent. So if I push this a bunch of times, it will have exactly the same behavior. Okay? Anybody confused? Can we move on? Yeah, go ahead. Oh, that's a great question. It starts at line 9. Um, the the IO interface does not guarantee that property. But in this case, that is what is happening. That's right. Yeah. And there will be more elaboration on that later. Yeah. Good question. Let me put the type in and then make sure I'm right here. So it's io.future. This is a type that you need to give it the type of the return type. So, and the return type in this case is void. So this should still compile, I think, unless I messed it up. Okay. So this is this type, and this type is the same with all implementations. Um, I'm going to stick to just looking at examples for the first part, and then in later, if you remind me again, we can go look at the implementation details. Okay. Yeah. Another good question. You're talking about down here, right? Yeah. Very nice observation. Um, Let me postpone the answer to this question because this example will answer it. And then if there's still a question, then we go back. Okay. Okay. Yep. Yes. Yeah. Similar concepts. I haven't used them in a while, so I don't remember what exactly the differences are. But I do know that whenever I try to use like the then method or error handling, I don't like it. So that part's different. Yeah. This one. It's a clock. So this is going to translate to yes. Yeah, the suspend one is called, well, I forget, but remind me, we'll look at the clock. Yeah. Yep. Okay. Ready to go to the next one? Nice. Yeah, keep the questions coming. It's nice. We have plenty of time to do interactive. Yeah. Okay. So what we saw is just splitting a function into beginning and end. Pretty straightforward. But let's start to add more real world situations here. So in the next example, we have um, two things at the same time. Okay. So let's see what it does. Actually, let me clear the screen so I can. Okay. Now these the work is waiting for 1 second. So if you watch carefully, if you count to one, it did not wait 2 seconds. It waited 1 second because these operations are happening at the same time. Um, so this demonstrates why using async await is useful because you can express in your code that you want to do. You can express asynchrony. So the fact is that doing this work here and doing this work here are independent. So you can express in your code that they do not need to wait for each other, and they can be done at the same time. And depending on the IO implementation that you choose, it may be able to take advantage of that concurrency that you have expressed and, sorry, the asynchrony that you've expressed and make your code run faster, which in this case it does because we've done 1 second of simulated work at the same time, which means we've done 2 seconds of work in 1 second of actual time. Does that make sense? Yeah. That's correct. Yes. So you don't get execution order when you do these things. And that's the point because when you express this, you're saying that the operation can happen independently. So then the order should not matter in that case. Right. Exactly right. Yeah. You said no op implementation? And you can get this effect by passing f single threaded. Okay. And so to answer your question, this one supports that use case with that flag. We can also, and I will show this example later because it's relevant, but you can also limit the CPU count like this. And I'll do that in example 8. Okay. Okay, so we just saw doing something at the same time. Now let's go to, wait, why do I not have example 4 open? There we go. Okay, so now in example 4, we're trying to make this even more real world scenarios, because in real world scenarios you have errors, you have resources, you have all these things. So in this example, we're simulating an error occurring in one of these examples. So this one, the first letter is H. So if that one we're going to return out of memory, um, and then uh, so it's the same code as before, except now this one will return error out of memory. Okay, now, does anyone want to predict the outcome if I run this example? Give you a few seconds to think about it if anyone wants to gamble. Oh, Felix. Bingo. Yeah. So this is a problem. It's exactly what Felix said. So to follow the control flow, so this one starts running. This one also starts running. The first one gets to here, returns out of memory. Control flow comes to here, and this try activates, okay? So then we fail to call this function. So we return from here, and then our leak check detects that we actually leaked this task. So this is a bug. This is a bug. So we have to fix this bug. That's unfortunate, right? Because you would like to write the code this way. Well, if we fix it, we have to write the code differently. Okay. So here's a fix. We have to do the awaits, then we have to try the results. Okay. And the rest of the code is the same. Now this will fix the problem. But it's unfortunate, isn't it? Because I want to write the code the Zig way, where I have I can just try await. This is a foot gun for sure. But this is the correct behavior because the first one, the second one worked. The first one returned out of memory, failed successfully. Okay. Well, here is where cancellation comes in. So cancel is a really, really nice primitive. So here's the change. After you do async, it's very common that you're going to kind of like if you allocate, you defer a free. If you async, you defer a cancel. And this is a really, really nice pattern because now we can use try await like normal. And not only do we prevent the bug, we also get more optimal code because look at how fast it executes now. It's instant because the moment that this one returns an error, this try returns. Because this try returns, we run over these cancels, and the one that's still waiting gets canceled. So the cancel is your best friend because it's going to prevent you from leaking the resource, and it's going to prevent you from, and it's going to make your code run more optimally. And one more thing before I call out, here's the semantics of cancel. Cancel, it's very simple to understand. It's exactly the same as await. Cancel and await are the same, except cancel also requests cancellation. And they're idempotent, just like await. Did you have a question? In this case, because we're using the debug allocator with the IO implementation, we get that for free, as we saw earlier, because if you forget to await something, then you leaked memory. So that check happens to catch the other thing. But you're hitting at something that's a very nice property that we can do. Because we have a place to store states, we can catch additional resource leaks. So for example, I'm showing you only timing and synchronization primitives right now, but this interface will also do networking, file system. Well, let's just start with networking file system. So if you leak a socket or you leak a file descriptor, then this one can catch this and report it, just like the leak checker can catch leak memory. Yeah, but you can keep going. Yeah. This one, the threaded DNet. Ask me again after the demo, and then we'll go into looking at implementation details. Yeah, we'll switch modes. Okay. Yeah. Um, sure. Let's take a look. So this is the idea, error defer. Um, I think it should always be a defer. So in this case, error defer will be fine. But because cancel is idempotent, so for example, and it's idempotent with await and as well. So you can call await, cancel, cancel, await, cancel. It doesn't matter. They're all after the first one. The second ones are all no ops. So there's two angles here. One is from the readability perspective. The defer is a bit easier to reason about because you just know that after you read these two lines, and how do you read the next line? You know that when we return from down here, anywhere below this defer, we know that this will never be referenced again. It's canceled. It's done. It's almost like you can just stop thinking about these two lines if you have the defer there. And then furthermore, I might just want to return early. Like maybe this function returns an integer or void or whatever. It doesn't matter. Point is, if you use defer, then you can just keep using all the normal control flow constructs for the rest of the function. Everything's fair game. You can use try, you can use return, anything goes. You don't have to worry about it. Yep, in the back over there.
Yeah, no, that or or
You should think of it like a resource, as if you had opened a file or as if you had allocated memory. It's like you've allocated a task as a resource. So maybe you don't defer it because later you're going to return it. That's also valid. Like you might open a file and then return the open file. Yeah. But as you can imagine, this is kind of more structured concurrency. So this would be a good way to start. And then not doing this would be more advanced because you have to, well, if the resource lives longer, then that's more complicated to reason about, right? Yeah. Over here, even the cancel, you run into,
work that made man you on that.
yeah, what's important to understand is that the cancel is a request. So the work may ignore the request, in which case there is no difference between await and cancel. It really just will then wait till it finishes. But ideally, the request is noticed, and then the work finishes faster. But you do not get a guarantee that the work finishes faster from cancel. You may just wait the whole time. Yeah. Can you store await? Can you defer await? Yes, because Yeah, that works fine. The only thing you can't do in a defer is control flow out of the defer expression. So you would not be able to defer try awaits because of the try, but you could do defer await. Yeah, that's no problem. But why would you defer await when you can defer cancel? Over here. That's a great question. You've halfway invented example 7. Uh, but I think the other half of your question, we'll do it again after that one. Okay, yeah. Felix? Oh, this
May up book to
yeah, the two errors here are clock unavailable and canceled. Yeah, so one thing I should mention here is that there's now m- many of the IO functions have error dot canceled and the error set. And this is what you would probably get here, and which we don't care about because we're returning. So what this means is that it's a very nice property because your your resource management code is handling errors, right? In the case of the error, you free the memory. In the case of the error, you close the file and you shut down all these things. And so because cancellation is an error dot canceled, you end up going through all of your resource deallocation code as you cancel. And then that probably that propagates the cancel to your callers. Yeah, was that the answer? Did that answer the question? Yeah. Yep. Yeah, the question is this illegal if there's any unawaited, uncanceled tasks, right? This is a this would be kind of an assertion failure. If you had any if you did async and then you never call cancel, you never call await, and then you deinitialize the IO or the threaded in this example, then this would be equivalent to a memory leak. Yeah. And it could have correct application specific correctness issues as well. So more important than a memory leak because maybe you needed that to finish in order to correct your data coherency or something like this. I think that this kind of well, this is an idea that can be considered. This is not how it is currently conceived. And my opinion, my first opinion considering this idea is that it's dangerous because um, the code should be managing its resources, and what you're describing is kind of like a queryable garbage collector, right? Well, okay, I wasn't, I don't have this in my examples, but one of the primitives that we have is a group. So then you make the group, and you can async in the group, and forget about it, and then later you can manage the group, and that's your kind of bucket. That's your arena, is group for tasks. Yeah. Yeah, over here. In almost all cases, you're going to get it for free because you're in your code. You're going to call, for example, like file.read, something like this. Now in file.read, there is a new error possibility, which is canceled. So you're doing work, third party requests cancel for your work. Your call to file.read now returns error.canceled. If you're just doing try, for example, you're now returning try up your function. You're freeing all your temporary resources or whatever, and you end up returning error.canceled yourself. So then that further propagates up. You see what I mean? So you're typically going to get cancellation completely for free. But you could also explicitly add a cancellation point if you want to. I think you will never need to do this. Yeah. Only in CPU bound code. Maybe you're processing 100 million objects, and if the iteration modulus 1,000,000 is 0, then you check for cancellation, something like this. Okay, ready to go to next example? Okay. Okay, so we looked at we looked at cancellation, which is the big one, and that cleaned up or where are we? That cleaned up our resource management. Okay, so next, yes, so next we're doing something also that you might have happen in real world code. Sorry, excuse me. You're allocating a resource and returning that resource from your function that is being executed asynchronously. So in this case, we will allocate a string and do work if it succeeds. If it fails, we do not allocate the resource, which means that if you have a successful call to the function, you need to free the resource and to free the string. Okay. So now we see why cancel and await are the same, except that cancel requests cancellation. Because now in the defer, we have to handle the success case. So if the call succeeds, we have to free the resource. And in fact, even in the happy path, we go down here and we print everything, we still go up and have to free the resources. So this code is handling both the cancellation path and the happy path. Well, it's handling the failure path, which includes cancellation and the happy path at the same time. So let's take a look at running the code. Example 7. Okay, so that's just running, again, 2 things in 1 second, except we manage resources along the way. So the point of this is just return value here represents a resource that has to be freed. We managed to free it correctly here. And underneath these underneath this block of code, the important point is that down here, we still get to write normal Zig code. We can still use try. We can still use return. You can copy paste code from a function that's not doing async into a code that is doing async, and it's going to work correctly. Yeah. Oh yeah, sure, sure. Like this. Yeah. Is this what you're observing? Sorry, line. Yeah, now it's fine because we properly did our resource management in our defer. Yeah. And we still have the property that if the memory allocation fails here and fails here, we don't bother waiting for the second one because we have the cancellation up here. Yeah. Ready for the next thing? Over here? Yes, but you will notice that this is a IO implementation specific API. So the IO interface does not require allocation to be how async is implemented. So
Mm, mm, mhm.
This is your answer. It's good. It's good. It's gratifying because it means that the progression is yeah, okay. Yep.
Well,
Yes, that will be copied. Yeah. So you would want to pre-allocate if it's a large return value. You want to have some different strategy for allocating. Maybe you pass it in as a pointer or something like this, and then you populate it. Yeah. And you can do this. Well, there's many ways to do it, but it's important to notice that with this pattern, you can reference stack memory here, right? You can pass this into, like, this is okay, right? We're not going to use the stack memory because this defer is protecting, because this will wait until this is done. Then we know that this is safe to do. Does that make sense? Yeah. Okay. All right. So let's go on to next one. Now we're switching gears a little bit. So it's time to learn why asynchrony is not concurrency. In this example, now we have instead of do work, okay, we have producer and we have consumer. We have a pipe channel queue, however you want to call this, with no buffer. So if you try to put into the queue, you will wait until a receiver can take the item from the queue, and then you can go back to work. Make sense? Now, now we're using async to spawn the producer, we're using async to spawn the consumer, and we're passing, we're just putting something in the queue here, we take it out of the queue here, and we print it. So just passing a little token along, just like that, okay? So if we run this succeeds incorrectly. This is a bug, even though it works. To observe the bug, we have to do something like this. We have to go in and edit our, this is the same example. We have to go in and add CPU count equals 1, limiting the amount of concurrency that the IO implementation can offer us. Now, if we take the same code, because it can only have one, it's only using one thread, we deadlock. Because the consumer is, sorry, we have only one thread, and yeah, the consumer is waiting to get something from the queue, and the producer is scheduled to run, but has not run yet. And we're waiting for this one to return, so we deadlock. The problem is that we asked for asynchrony, but we needed concurrency. So in order to fix this, we use io.concurrent instead of io.async. This one can fail. So the setup is the same. We now still have only one CPU available, but now we use concurrent. Now the code is fixed because we correctly expressed that we needed concurrency. And if I add single threaded, which is different than this is passing because the threaded implementation will oversubscribe the CPU, which it's allowed to do with this. When I pass f single threaded here, it will only use one thread. It can never oversubscribe. And so now we get an error, concurrency unavailable from here. So instead of the deadlock, we get an error that we can handle and do the code differently. Yeah. That could be a nice idea. That's not something that I've put in the interface yet. But maybe it could be something that you know at runtime, because, for example, if you're using a thread pool, you have concurrency up to the pool size. And then if you want more, you have to oversubscribe. And the thread pool does not want to oversubscribe because that's inefficient. But if you ask for concurrency, then it will oversubscribe. So if you're asking, well, do you have concurrency? Then what's the answer? Well, the answer is kind of, maybe you actually should error if thread pool is full. Maybe that should be configurable. Yeah, but that's how it's currently implemented. That is a decision that the API, the IO API, could make one way or the other. And yeah, I mean, I'm not sure, 100% sure what should be the final way, but the way that I've made now, that what I would like to do is to have people try this out in their real world examples and then tell me, how's this working for you? And so the first proposal or implementation that I'm providing to say, hey, try this out, is this one, where you get an error if you ask for concurrency and you can't have it. Yeah. And you really should use async if you can, right? Because to finally answer the question over here, the other one does not fail because if it cannot allocate memory for the task, it will immediately call the async function right there. Does that make sense? So in this case, it has to run concurrency. But in the other case here, if this memory allocation cannot happen in order to allocate the producer, it will just run this function right here immediately before proceeding to the next line. And that's allowed because this is async and not concurrent. That's why there's no try here. Okay. Yeah. Let's try that. This one? So we may have run into an implementation issue here. I may need to examine the threaded implementation and look at how I've done like oversubscriptions and concurrency and things like this. So I'm not sure if this is a correct answer to the question. Yeah. Yep. Okay. So let's run through this. So this one is calling concurrent, in which case the threaded implementation will simply increment a requested concurrency counter and then schedule the producer. And then what'd you say? Oh, wait, I also did this. CPU count is 1. Do you think the consumer is running before the producer? Yes, but it is required that the producer will be running concurrently. So if the consumer runs first, then the consumer waits for the get, but the producer is then supposed to be concurrent. So then this code needs to eventually run, in which case this will then unblock the consumer and then everyone can proceed. Yeah. Yeah. This is the end. Do you guys want to come down for the QA? Yeah. Microphone and face the audience.
I was looking at that. So oh, you've got it there. That's a good point. Please hold while I try and clip this on properly.
So we can pass it to me.
Oh, right. Is there only one? Sorry. So I'm pretty sure what's going on here is that the So yeah, the producer is definitely running, but this put one's going to block until the get one call, I'd imagine, right? Depends on your implementation. So then I assume that the async is then refusing to spawn the thread. Like you were saying, this is an implementation thing. This is to do with how the threaded implementation is dealing with async when it's already maximally subscribed.
Yeah, I think I just need to revisit the oversubscription code.
Yeah. And this is, yeah. So this is, to be fair, I don't know how clear the interface documentation makes it, whether this should work. But that's a detail we can hash out.
Yeah. What is certainly a bug is to do the opposite. So if you put async at the top for producer, then async might decide to run. It does not guarantee that you continue executing the main function immediately. And that's what concurrent also guarantees. Concurrent guarantees that you don't stop. Like if you need to schedule more stuff, they will unblock what you just spawned. Then with concurrent, you're guaranteed that your function keeps running. But with async, we might decide to just stop there in the single thread case, for example.
Yeah, I think I just realized the bug I made, but that's exactly right. Yeah. What's the question? You want to look at the queue implementation? Oh, like a safety feature, detect deadlock. I don't know if it's possible because the queue is many producer, many consumer thread safe, and so maybe there could be another producer somewhere that would put it in there.
I think the more general answer is we do plan to have implementation of async of I/O for testing purposes, where we plan to add more checks and maybe even support fuzzing, so make its scheduling decisions deterministic based on a seed. But exactly what it is that we can catch or not, we don't know fully yet. Can you show? Yeah, can you show the source code? No, we're doing the second one.
There's an oversubscription.
Wait.
Yeah.
Does it not run stuff right away?
You've got this one Brexit cái little space for the or with the bigger called by Brett Honda. It that we have the blah blah.
Can you show it? The implementation of async?
Of async? Yeah.
Because I believe that we do just call the function right away, right?
No, only on memory failure.
Only memory failure. Yeah, there we go.
Yeah. To be honest, Felix, I couldn't follow everything you said, but I think this is not too bad to fix. Like, with this example in hand, it's just some bad oversubscription code. Yeah. Yeah. Over here. Select. Yes. I did not prepare an example for this, but now we can look at some source code. Here, let me make a big window and make the font bigger. There we go. So let's look at some of the primitives that we have here. I think that's a good one. So first of all, there's a select function. That's a different one. So I'm sorry, this is implementation code. It's not example code. So it's a little harder to follow. But you call io.select. You give it a union of futures, and then you can switch on the results, and then the one that wins the race is the prong that you can that has the result.
You said you give it a union. You said you give it a union. I think you meant you give it a struct, and it returns union.
You give it a struct of futures, and it constructs a union with this reflection code, and which then you can switch on to get the resulting future. Thank you. Yeah. Yeah, I did not prepare an example for that one. And then there's also a, so that's if you have, statically you have this set of futures, and that's kind of like a syntax you can use. It's more handy. The other one is if at runtime, maybe in a loop, you're adding things to a select and you want to know which one wins. So for that one, there's this API where you do give it a union. And the union is the type of return values of the function. I didn't prepare an example for this, I'm sorry. But okay, point is you can construct as selects, and you can call async on this one. And so you can do this in a loop. And then you can wait to find out which one wins, and you can do this multiple times. And this is an abstraction that's built on top of a group and a queue. So you could actually implement this yourself just based on these primitives. So group, let's look at group really quick. Again, this is implementation. It's not example, but group is is a really handy primitive. So it's kind of it's the arena of tasks. So you initialize the group statically. You can call async into the group. I think we'll add concurrent to this too. I didn't add that one yet. And then you can wait on the whole group together. And that's going to be more efficient than doing, a whole bunch of futures heap allocated or something like this, because it's just a counter instead of multiple resources together.
One distinction between group and arena, which I think is worth calling out. And to be fair, I don't know if you have actually documented this in your version. I did in my variant of the branch. We've worked on this kind of together over a while. But I think generally we intend that if you have a group and you put a bunch of tasks, start a bunch of tasks in it, asynchronously or concurrently, when they finish, the resources associated with that task can actually be cleaned up immediately, or at least once. Immediately. This is desirable because it means that you can use groups for kind of long-lived things. So if you have something like maybe some kind of HTTP server and you want to spawn like a task for every client that connects, then it's fine. And you don't need to keep track of all the individual tasks that are happening. It's fine to just put them in one group, and you're not going to leak resources over time because they will be cleaned up when the individual tasks finish. So that's kind of one distinction with an arena where, if you just keep using an arena forever, it's not magically cleaning up resources for you. You are slowly leaking memory.
You want to take this one?
I'm happy to take this one. The short answer is no. Next question. No. So firstly, it's not like you're going to be writing IO implementations all over the place. Like, the fact that you can have different ones is really helpful. We expect there to be several in standard library for kind of testing and debugging, and ones that use different strategies for concurrency. But when you're doing that, usually you're going to be writing, a big file with that implementation. So you don't really gain anything from being able to declare the functions in line. In fact, all you get from that is 2 extra levels of indentation, which doesn't really help anyone, compared to just declaring it in the file. Also, Andrew doesn't like anonymous functions, and so he made this decision a while ago, and I don't think he's going to change his mind on that one.
Oh, it was anonymous function syntax question. Sorry, I thought you were talking about function pointers. Okay. Yeah.
Oh.
Oh, nice.
This seems closer to what you thought was being asked, I think. Do
Yeah.
you want me to take the?
I'll do this one.
Okay.
So what you're actually passing around is these two things, and it's kind of what this is called a fat pointer, basically. So it's a pointer. It's 2 pointers. So that's kind of what you're passing around, and that's very similar to what you're passing around with allocator. So it's the same thing. Actually, let me just show that. So uh, allocator is also an interface, and there's your fat pointer right there. So it's kind of the same thing, and it's the same way of doing an interface. So it's just not that bad. For free floating functions, it's just not that bad. And then for in other cases, let me show you. Let me show you just a real world code base. So here's compiler. We have a lot of imports. We have a lot of fields in the compiler. So this is compilation. Okay, and here's where we keep our allocator right here. Actually, we have 2. Here's another one. And then here's where we keep our IO. And we're all familiar with this kind of object, right? Like you have a bunch of functions, and all the functions. Why did I not find a function? There's functions in this file, right?
Using ZLS.
There are quite a few functions in this part.
Yeah.
Well, that's not how function syntax in Zig works.
Oh yeah, I forgot function syntax. Let's just search for pub. Okay. So the point is, like, all these functions are going to take a compilation, right? There's one. That one's free floating. There's one. You get my point, right? Like if you have it's very common that you take your context structs as your first argument, and that's where you're going to have your allocator. That's where you're going to have your IO implementation. You probably only have one for most of your stuff, and then yeah, sometimes you have some free floating functions that are going to have an IO or an allocator or both. Yeah. Feel free to let me know if they have any follow up on the chat. Yeah, Adrian. I've been calling you Adrian Ariadne, right? Wait. Okay. Oh, I'm sorry. Experts. Yeah. You came in the hotel this morning. I was like, hey, it's Techatrix. What's his real name? And he's like, I don't know.
I'm out. But imagine, yep, we will see that. Con bò bạn tôi có go about of the hat maybe but
Right. Yeah. 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 What you're describing is a fun trick you can do if you have concurrency, but you can't actually express that pattern with async. You have to use it with concurrent, which, as you pointed out, has the weakness that it doesn't work that way. So yeah, in reality, I think it's better to also have in the IO interface, we have timeouts. So for example, I mean, sleep is your classic timeout. That's all it's doing. But also in, for example, receiving connectionless packets from the network, you can have a timeout on that. And so, yeah, exactly like you said, this means that this function can be used in like single-threaded, non-concurrent contexts, and also will work fine in concurrent contexts.
So the general idea is you bake the timeout into the operation.
Yeah. Felix?
mình có một cái ba sẽ một cái mặt
So that you can, under this condition, would you have access to concurrency where you could do this trick with a timelet?
Yeah. But I think this is an implementation detail because yes, but no, my point is you can, let's say that you want, let's say your point is you want you want to be able to cancel on a timeout a file system read. That's fine. It's not something that necessarily I think has to be in the interface, because I think this can be done with signals, for example, in single-threaded mode. As in the IO interface manages the timeout using OS APIs that don't require you to have concurrency. So I'm not sure if that happens in all cases. But my point is that there are some other tricks that can be done. Like, and it's not necessarily that every function needs to have timeouts, but maybe that is the better design choice. I don't know.
it would need to go in the interface if you wanted to be able to have a timeout in an application that did not have access to concurrency. Yeah. Are you thinking of an example of that? Okay.
Yeah, but it is fair. Yeah. Like, let's say that you want to read a file and the file is on a network device that's timing out, and so it's taking forever.
This would be a good time to talk about how cancellation works in the threaded mode. I think that's an interesting topic. Are we trying to fill time, or are we trying to hurry up and finish?
Yeah.
Okay.
Yeah.
Well, I'll keep it short then. So you can actually interrupt blocking syscalls by sending a signal to the thread, and then it returns enter, and then you can check for cancellation. So you can build this pattern that Techatrix is talking about, where you have a timer and then you cancel the file system operation.
And you can have, I think there's a timer API, like a timer syscall that can wake you up with a signal. At least on Linux, right? A timer D or something like this.
But the question, if you want to be able to run code without concurrency, single threaded blocking, no threads, and you want file system reads to time out, then it does need to go in the interface.
That was just a final one point. Is that it all?
Okay. Can I to say something?
Yeah, there was just a thing I wanted to end on. If you've got anything else to say, then go ahead. But I just want to say this interface is obviously something we've been working on. Where Andrew's been working a lot on the PR to get this initial version in. Pretty much none of these details are like finalized. So I say that partly as a warning. So if you want to start using this stuff itself, you go ahead, but know that you're opting into probably some instability in the near future. But also as like an invitation to get involved in this. We are not perfect. There are going to be use cases that we miss. There are going to be design ideas that we fail to consider. If there's ideas you have about how this interface should work, what primitives we should expose, things like that, you could join the compiler development Zulip server and get involved there. That's very active with discussion on how this interface should work, as well as all kinds of details of what we're doing with standard library compiler.
But bring use cases, not bike sheds.
Yes.
Yeah, more specifically, if you have an idea that arises from trying to use these APIs in a project and then you run into a problem, definitely want to hear that. If you're just kind of scratching your chin and speculating, yeah, maybe go write some code first and then come back,
Yeah.